Good morning, everyone. On the menu today, we are talking about chapter 17, actually a little bit of chapter 16, reviewing some anatomy, some concepts from anatomy, Bio 31, giving us a foundation to talk about the pulmonary physiology or the functionality of our lungs in chapter 17. Most of the lecture outline is on chapter 17, but we need to go back to chapter 16. So I will share with you um, when we talk about chapter 16, as it's basically shown on your learning objective there. So for starting with chapter 16, we're going to go and review back what is a volume, as seen up here, and what is a lung capacity. So once we define these two basic concepts, lung volumes and lung capacity, then we can understand much more thoroughly concepts from chapter 17. So with that said, what is a lung volume? So you can find lung volumes and lung capacities in your book, the Stanfield official textbook. And that's on page 467 of your book. So on top of the page 467, you'll see lung volumes and lung capacities. So let's start with the most simple concept, the tidal volume. Tidal spelled Tidal over here. That tidal volume is around half a liter, or 500 ml or 500 cc's. This tidal volume is the amount of air that's being displaced with each breath at rest. So basically, we call that a quiet breath. So at rest, you take around 12 breaths per minute. So each time that you're inhaling, you're breathing in, and you're breathing out, exhaling, you're moving in and out of your lungs half a liter or 500 cc's or ml of air. And we call that quantity of air tidal volume. Okay. The next one is called inspiratory reserve volume, IRV. This inspiratory reserve volume is the amount of air that you can forcefully breathing in right after that tidal volume. So when you breathe in normally, and after at the end of that tidal volume, at the end of that inspiration at rest, you forcefully inhale more air into your lungs. We call that inspiratory reserve volume. And that volume is around 3 liters or 3,000 ml, okay? So air that can be inspired or inhaled forcefully after a tidal inspiration. So following a tidal breathing in at rest, then you forcefully push more air into your lungs. That's an additional 3 liters on top of the half a liter that you breathe in at rest. Okay? So that's basically 3.5 liter total volume with inspiration reserve volume. And that is over here, we call that functional residual volume. No, inspiratory capacity, sorry. Okay, so that's the amount of air that you can bring into your lungs, breathe in. You can also kick out a defined amount volume of air. We call that expiratory reserve volume. And this volume of air here is the amount of air that you can kick out, you can expire, you can breathe out after the half a liter that you breathe out at rest. So after the tidal expiration, meaning the half liter you breathe out at rest, Now you forcefully breathe out more air out of your lungs, and that additional amount of air that can be breathed out, expired from your lungs is around 1 liter, right? So that we call that expiratory reserve volume, air that can be expired forcefully after a tidal expiration. And the fourth type of volume, the final type of volume, is called a residual volume. This is around 1200 cc's or 1.2 liter. This is important. This is the volume that cannot be displaced, right? This volume remains in your lungs. Remember, for anatomy, we have 2 lungs, the right lung and the left lung, right? So that amount, 1.2 liters, it has to remain in your lungs. If you lose that volume, the consequence is your lungs will collapse, right? So if you have a punctured wound, for example, that residual volume basically escapes from your lungs, depending on which side of your lung is being punctured, either the right or the left, then that particular lung that has been punctured would basically completely collapse because of that residual volume. What's keep the lungs inflated is the residual volume, 1.2 liter of air that remain in both lungs to keep them inflated. So we cannot afford to lose that volume. You lose that volume, your lungs collapse. So that's the basic definition of the lung volumes, the 4 lung volumes: tidal volume, inspiratory reserve volume, expiratory reserve volume, and residual volume. If you add these different volumes, we have another concept over the right-hand side. They are called lung capacities. So lung capacity is simply the sum of 2 or more lung volumes. So the first one, inspiratory capacity, that's the sum of the tidal volume and the inspiratory reserve volume. So half a liter plus 3 liter over here equals 3.5 or 3.5 liters, or 3,500 cc's or 3,500 ml of air. The functional residual capacity, that's the total amount of air in the lungs after the tidal expiration, right? So that's the sum of the RV plus ERV. RV is the residual volume and ERV is the expiratory reserve volume. And then, so that's around 2,200 cc's or 2.2 liters of air. And then the vital capacity, this is an important volume. This is an important number, 4.5 liter. This 4.5 liter is the amount of air that can be exchanged, that can be, usable, okay, displaced. So that we're talking about the tidal volume, the inspiratory reserve volume, and the expiratory reserve volume. So the top 3, half a liter plus 3 plus 1, that's 4.5 liters of 4,500 ml, 4,500 cc's of air that are available to be displaced, to be exchanged, okay? If you add that vital capacity to the residual volume, so add another 1.2 on top of 1.5, you end up around 6 liters of air. So we call that total lung capacity. So the total lung capacity is the sum of all 4 lung volumes, whereas the vital capacity is the sum of the top 3 volumes, excluding the residual volume, right? So the top 3 volumes are the amount of air that can be displaced. The 4th volume, the residual volume, this volume has to remain in our lungs, okay? So vital capacity is important in the sense that's the amount of air available to be exchanged, to be breathed in and out of your lungs. Whereas the total lung capacity, the difference between the two, the total lung capacity is the vital capacity plus the residual volume. That's why it's around 6 liters of total amount of air that are contained in both of our lungs. So that's a summary of the lung volume and lung capacity. And down here, the third panel, this is the graphic, and that's also from chapter 16. And that graph is from figure 16.16 on page 466. On the left-hand side, it shows you the lung volumes, and on the right-hand side, it shows you the lung capacities. So again, lung capacity is just a sum of various lung volumes. So you have here that little drawing, that's your tidal volume. So being displaced only half a liter. This amount here, that's inspiratory reserve volume, IRV. And this curve down here, that's ERV, expiratory reserve volume. And the last one, the residual volume here, that's the air that has to remain in your lungs, right? So those are the 4 volumes: TV, tidal volume; IRV, inspiratory reserve volume; ERV, expiratory reserve volume; and RV, residual volume. And over here is the sum of different volumes. The inspiratory capacity is the sum of the TV and the inspiratory reserve volume. So that's the sum of the two. Whereas the functional residual is the residual volume with the expiratory. So that's over here. And the vital capacity is all 3 up here. So tidal volume plus inspiratory reserve volume plus expiratory reserve volume, that's your vital capacity. And then the total lung capacity is all 4 volumes together, okay? So vital capacity, this big arrow here, plus the residual volume on this side equals total lung capacity. Now we move on to chapter 17, the physiology of our respiratory system. So we're going to go over how gases are being transported in our blood plasma and also red blood cells. And we're going to briefly go over how is the ventilation being controlled. So ventilation control mechanism, okay? Now let's go over on the next slide. Let me try to start the annotation here. Hello. There you go. Now, in the clinical setting, there are quick and easy functional tests for our pulmonary performance. So when we say P ventilation means pulmonary ventilation, pulmonary functional test, quick and dirty. This can be done by attack, when they come, when you call the ambulance, all these technicians, EMS, can basically perform these tests. It's quite simple. But these simple pulmonary functional tests can give us some parameters. So they can tell us, for example, whether the patient has, we can differentiate 2 conditions: obstructive pulmonary disease or restrictive, conditions. So obstructive versus restrictive, right? So what's the difference between the two? obstructive pulmonary disease, this is caused by an increase to the resistance. So the resistance to airflow has been increased. So the patient is having a hard time inhaling air into his or her respiratory passageways. Whereas the restrictive disorders, we're talking about a significant decrease in total lung capacity. So his or her lungs, the total amount of air that is in the patient's lungs has been drastically reduced. So for example, we can talk about instead of having 6 liters of air, that patient contains around 3 to 4 liters of air. Okay? So the amount of air in the lungs is dropped up to 50%. So what are the exact conditions for these two? So in the case of obstructive pulmonary disease, we talk about emphysema, we talk about chronic bronchitis, those examples in a clinical setting and they fall under what is called chronic obstructive pulmonary disease. And you know that as COPD, right? So the COPD conditions are basically involving an increase in terms of resistance to airflow. Whereas restrictive disorders are involved in the compliance. So the lungs or the chest, the chest walls are basically less compliant. So the less they can basically, in terms of expanding the chest or compressing the chest, is less compliant. So we're talking about, for example, pulmonary fibrosis that would lead to restrictive disorders. So in decreasing total lung capacity. Now, we test them quickly by two conditions called FVC and FEV. The FVC stands for forced vital capacity, whereas the FEV stands for forced expiratory volume. And this forced expiratory volume, we can ask the patient to forcefully breathing out, and we take the measurement at 1 second, right? So in other words, how much air can the patient breathe out during the first second? That gives us an idea about the condition of his or her lungs. For example, if for the first second, this stands for F, we're going to mark that as FEV1. So if the patient is breathing out during that 1 second, 80% of the air that it was in his or her lungs, then the patient's pulmonary function is normal. But if the patient suffers obstructive pulmonary disease, increase in terms of resistance to airflow, then it will not display 80%. It will be much, much, much more lower. Okay. Whereas the capacity here, the forced vital capacity, if it's low, then it shows it's indicative of the restrictive disorder kind. So this is due to a decrease in total lung capacity. Okay, so a low FVC is indicative of restrictive disorders caused by a decrease in total lung capacity. But the obstructive pulmonary disease will be indicated by a low FEV. V1. Okay. So I'm going to erase this. We're going to go back to this, I think in the next 1 or 2 slides. Revisit this with the graphs to show you in more detail about this quick and dirty tests. Now, when we say minute ventilation, this is the amount of gas flowing in and out per minute, in and out of our lungs or respiratory tract per minute. So like I said earlier, normal breathing at rest, we are taking about 12 breaths per minute. So each breath lasts around 5 seconds. And in that minute, there are 6 liters per minute. So we are breathing out half a liter per breath, right? So that's the tidal volume. If we have 12 breaths per minute, so 12 times 500, that's 6 liters per minute, right? So you are at rest displacing 6 liters per minute. But what is amazing about our pulmonary capability is this. When you are under vigorous exercise, that 6 liters will be increased all the way to, so this is 6 liters per minute. Okay, so at rest, you are displacing 6 liters of air in and out of your lungs for every 60 seconds. When you exercise, that number, 6 liter, will be increased up to 200 liters of air per minute. That's an incredible amount. That's more than 30 times from comparing to the amount of air being displaced at rest. Okay? Now, what is not obvious is more important than the amount that comes into the lungs is the concept of how many of that volume is available for gas exchange. This is important here. It doesn't really matter if you have a lot of air going to your lungs, into your respiratory tract, but if that air, most of it, it will not get into your alveolar surfaces, each alveolus, then you're not getting any gas exchange, right? So because throughout that respiratory tract from your nose all the way down into your alveolar surfaces, alveoli, gas exchange only occurs at the alveoli. So from your nose, trachea, primary bronchi, secondary bronchi, tertiary bronchi, subsequent bronchi, the branching up to 25 times, but before it gets to the alveoli, all of that air is not exchangeable. It's just flowing by that respiratory tract. But our internal organs or blood vessels cannot have access to that air. We have to wait until that air gets into our alveolar surfaces before we can exchange that gas, before we can kick out carbon dioxide and get oxygen inside our blood vessels, right? So because of that, it's important to not measure really the ventilation per se, but we have to focus on alveolar ventilation, meaning the actual amount of air that get to the alveoli, right? So measures flow of gas in and out of the alveoli per minute. So what we have is dead space, the concept. Our respiratory tract Any part of the respiratory tract that has no capability for gas exchange, we call that a dead space. And that dead space is around 30%. So if you inhaling, you're displacing 500 ml of air during a tidal volume. Of that 500 ml, there's only 350 available for gas exchange. Okay, only 70% is available for gas exchange. Okay, so if you are bringing in 6 liters per minute, 70% of that, there's only 4.2 liters of air available for gas exchange. The other 1.8 liter is basically in the dead space. Your nose, your trachea, primary bronchi, secondary bronchi, tertiary bronchi, all the bronchioles, including the terminal bronchioles, before you get to the alveoli, not available for gas exchange, right? So that's an important concept. So how much air is actually getting into our alveoli? So whatever the amount of you're displacing, only 70% of it is available for gas exchange, because only 70% of that air can have access to alveolar surfaces. Okay. Now this is going back to those tests that we talked earlier. Starting with the forced vital capacity. So if you have, so this is the norm in a normal patient up here. So this is the volume being displaced up to 4 liters, right? So forced vital capacity, 4 liters. This is the condition where it shows clearly a drop. So this is at 4 liters. This is around 2 liters. You see this line here versus this line, you clearly see a drop in terms of volume being displaced or breathed out. So it shows you a restrictive condition. Okay? So decrease in TLC, total lung capacity, displaying low FVC, forced vital capacity. This is, for example, you see that in pulmonary fibrosis. Okay. Moving on to the next test. This is the amount of air that the patient can breathe out for the first second. So this is the normal patient, right? For the first second, you get around, this is total 4 liters, this is around 3.2. So that's 80%. This point here is 80% of the amount of air that has been displaced for the first second. When your patient is breathing out, exhaling, it took only 1 second for the patient to basically breathe out 80% of the amount of available air in your lungs that can be displaced, that can be breathed out, if his or her lungs are normal. In the case where the patient is suffering obstructive disease, meaning the resistance to airflow in the patient's airways has been increased, then you can see here, the point is right here. So that's a drop right there for the first second. and that's a condition indicative of obstructive pulmonary disease. For example, emphysema or chronic bronchitis, right? Now, one thing your book is not really clear on this is the following. And this is also another example where you can clearly compare the two. If you look closely on this panel here, you can see also clearly that obstructive, even though the first second, the amount of air that gets out is significantly lower, but if you allow enough time, the lung is still capable of getting a normal forced vital capacity. So in the case of obstructive, the forced vital capacity is the same as the normal patient. But in the case of restrictive, you cannot have a forced vital capacity as high as a normal patient, right? So that's why you see the difference here for the two cases. The restrictive FVC is completely being compromised. You will never, that patient will never be able to have that total lung capacity that we mentioned earlier. Okay, again, so to summarize this, obstructive conditions will lead to a low FEV1, okay? Low FEV1 for obstructive conditions. Whereas the restrictive diseases will indicate a low FVC, okay? Force volume capacity. Forced vital capacity, sorry. Okay, so here, restrictive, low FVC, okay? Obstructive, low FEV1. Again, restrictive disease, low FVC, obstructive disease, low FEV1. Now, we are for the first time dealing with chemicals, but not chemicals dissolved, you know, in water. It's like this is, we're talking about gas state here. We're not talking about liquid state. So we need to go back and define some behavior. For example, how does a gas behave in liquid? Or how do gases interact with one another? Okay, so we're gonna go over basic characteristics, basic features, basic properties of gas. For example, how do they interact? Do they mix with one another in a mixture of gases, or do they ignore one another? So are they interacting, in other words? So there's a law, we call it Dalton's law. This law allows us to basically, how do I say this? Gives us an idea of the pressure in a gas, the contribution of each gas member to the total pressure in that compartment. For example, the total pressure of a gas mixture is actually the sum of all the partial pressure contributed by each gas present in that mixture. Okay, so for example, the air in the atmosphere, ATM here stands for the ambient air. That air contains a mixture of different gases. Nitrogen, that's the most abundant in the air, around 80%, slightly less than 80% is nitrogen. Less than 20% is oxygen. And then trace amount of carbon dioxide, water, and other gases. Okay. So contributing ambient air is actually, oxygen is around almost 21%, 20.9%. And what is important here is that percentage is constant. The 20.9% is constant, whether you are at the sea level or you are at in high mountain, like 10,000 feet above sea level. It doesn't matter where you are in terms of elevation, that percentage will not change according to Dalton's law, right? If it's the same gas mixture, in this case, ambient air, right? So that air at the sea surface, sea level, or that same air 10,000 feet above sea level, it's the same air with the same gases. If that's the case, then the contribution of each gas in that total mixture will not change. For oxygen, it remains 20.9%. So because of that, at the sea level, you have 159 millimercury of oxygen. But high in the mountains, the air drops in terms of the concentration of the air. So it drops from 760 to 523, right? So there's less air at high altitude. So what's going to happen is the oxygen also will drop. Although the percentage stays the same, but the absolute amount of oxygen will drop. You see here. So it drops from 159 all the way down to 109. So the higher you go in terms of altitude, the lower the oxygen content in that air that you breathe in. So that's why athletes, they train at high altitude, because they know you go high in terms of altitude, there's less oxygen. And when that happens, the body responds. To maintain homeostasis, the body will produce more red blood cells naturally without doping to compensate for the less amount of oxygen available for gas exchange. So the body compensates by having more red blood cells. So to increase the body's capacity to transport oxygen. And when that athlete goes back to sea level for competing, that athlete has an advantage over his or her competitor, opponents, because now that athlete has much more red blood cells available. So that athlete's capacity to transport oxygen during a competition is significantly higher than his or her neighbor who didn't practice at high altitude. Okay, it's because of that same concept. Even though the amount of oxygen is less, the percentage in that mixture remains the same. And we call that Dalton's law. So Dalton's law is basically predicting how gas behave in a mixture. How do the gas interact with one another, and how each gas is contributing to the total pressure within that mixture containing multiple gases. So that's Dalton's law. The second law allows us to predict how gas behave in solution. How do they move in and out of water, right? So life is the solvent of life is basically water. So we are talking about how do gas behave in water, relevant for life. And that's described by Henry's law. So we are talking about solubility factor here for a gas, because not all gas, each gas has a unique solubility factor. For example, CO2 is around 20-fold more soluble in water than oxygen. That's why you have carbonated drinks. That's why, for example, Pepsi, 7-Up, Coca-Cola, they are using CO2 instead of oxygen, because CO2 is like 20-fold more soluble in water than oxygen. So when you shake that up, that's why it's called carbonated, because it contains all these drinks, soft drinks, they contain carbon dioxide instead of water, for the simple fact that carbon dioxide is much more soluble in water than oxygen. So oxygen is around, compared to CO2, 20 times less soluble in water. Nitrogen is even worse, 40 times less soluble in water than carbon dioxide. And when we talk about solubility of gas in water, we can increase that solubility or decrease that solubility by playing with the temperature of the liquid, of the solvent, in this case of the water. So if you increase the water's temperature, you will decrease the gas solubility. So in other words, if you increase the temperature of the liquid, the gas has a higher tendency to escape the liquid. Okay, so gas solubility will decrease as you increase the temperature. So the relationship between the liquid's temperature and the gas solubility is inversely proportional. The higher the temperature of the liquid, the lower the gas being soluble in the liquid, because you are basically giving energy to that gas to escape from the liquid. That's why when you basically boil water, water basically evaporates. That's exactly the same concept. So when you boil water, you give the water energy, and that energy increases the kinetic energy, meaning the motion between the water molecules, to the point where they can basically overcome the surface tension, and then they just escape. They become gas state. Instead of water, now it becomes water vapor. So that's the same concept. This is predicted by Henry's law. Okay, so moving on here. So this is this next slide. There are two slides in this outline where it's the heart and soul of the entire outline. It's understanding how oxygen and carbon dioxide are being transported in our cardiovascular system. In other words, how can they be exchanged, and then how are they transported from the lungs to your systemic tissues, and from the systemic tissues back to our lungs. Okay, so let's start with oxygen. Oxygen there's only two transport mechanisms for oxygen. Since oxygen is really poorly soluble, only 1.5% of oxygen is being transported as is in blood plasma. The remaining 98.5% of oxygen is being transported by hemoglobin. This is a protein that is inside each red blood cell, and it has its job is to transport oxygen. And to refresh your memory from anatomy, a hemoglobin has 4 subunits. So it's a protein complex. It's not really one single polypeptide chain. Each hemoglobin consists of 4 different protein subunits coming together So hemoglobin displays a quaternary structure, and each protein subunit transports one oxygen molecule. So each hemoglobin transports 4 oxygen molecules. And what is amazing is within each red blood cell, you have 300 million hemoglobin proteins per red blood cells. Okay, 300 million. So in other words, each red blood cell transport up to 1.2 billion with a B oxygen molecule. So the number of oxygen being transported by our red blood cells is a humongous, mind-boggling number. It's a humongous number. Now, how is it possible for oxygen gets from the alveolus here and into the red blood cell and gets transported? There's one equation that will follow you for the rest of your clinical career, okay? And it's shown here. The relationship between CO2 and this CO2 directly affects the pH of a solution. This is a very important concept. Okay? If CO2 increases, pH drops, and vice versa. If CO2 decreases, pH increases. I plead you not to memorize this. You know me by now, right? I will trick you so you will fail the test. So understand the concept. So here comes the concept, okay? I say that each semester, and every semester, there's always individual students who basically blindly memorize what I just said, not listening to my suggestions, and then they get trapped during a question at the test. So here it comes. Oxygen will move directly from the alveolar space. This is coming from the inhaled air. It gets into the red blood cell. Once it gets into the red blood cell, oxygen interacts with hemoglobin, right? So oxygen interacts with protonated hemoglobin. Okay? And when that happens, the oxygen binds to hemoglobin and it displaces the proton. So you're gonna say, okay, where is this proton coming from? This proton is over here. And when that proton is displaced, you never want that proton to be freely floating because that proton will affect the pH of its surrounding. So what's going to happen is this proton, the cell, the red blood cell, to protect itself from acidification, it will force this proton to interact with bicarbonate, HCO3 minus. You see it right here. That's the interaction right there. Okay? To prevent pH fluctuation. So this is a buffering mechanism. So bicarbonate binds any available free floating protons. As soon as you have free floating protons, the pH of that solution will drop, because if proton concentration increase, pH drops. Okay? You don't want pH dropping in your red blood cell, because the red blood cell will die. That's why bicarbonate comes in. Now, where did that bicarbonate come from? That bicarbonate came from blood plasma. So when that bicarbonate gets into the red blood cell gains a negative charge. That negativity has to be exchanged. You don't want a net charge in anything, right? So all our cells, all our surroundings are neutral. We're not talking about the plasma membrane here. We're talking about the entire cell. So if the entire cell gains a negative charge because of the entry of the negatively charged bicarbonate, then the cell will exchange by losing chloride out to the blood plasma. So it gains a negative charge, it loses that negative charge to keep it neutral. And that concept, we call that reverse chloride shift. Okay? So chloride is leaving the red blood cell to compensate for the gain of negative charge brought in by the bicarbonate. And when that happens, when bicarbonate binds with the proton, it will become carbonic acid. So H2CO3, that's called carbonic acid. C-A-R-B-O-N-I-C, the word acid. And that carbonic acid is basically dismantled into water and CO2. And you see where I'm getting at. That CO2 now will go into the alveolar space where you're breathing out. So this is amazing. When oxygen comes in, it induces CO2 being released back into the alveolar space. Okay? And later when you're going to learn about this bicarbonate, you should have asked, where do we have this bicarbonate? And magically, this bicarbonate, this is how the body transports CO2. 70% of carbon dioxide is being transported in the form of bicarbonate in blood plasma. All right? 70% of all CO2 in the body is being transported not in the form of CO2, in the form of HCO3 minus. So when that HCO3 minus gets into the red blood cell, ultimately it has two functions. It prevents pH dropping because of the presence of free floating proton, but also it helps itself when it neutralizes that proton, it helps itself to drive the equilibrium toward the production of CO2. Because this relationship here, it involves two equilibria. There's one here, it goes both ways. And there's another one here, it also goes both ways. So we have two equilibria involved here between bicarbonate, proton, and carbonic acid, and between carbonic acid and CO2 and water. So if you increase on one end, you drive the equilibrium to the opposite side. So if your proton is increased, bicarbonate is increased, then it drives the reaction toward the production of CO2 and water, and CO2 simply diffuses out and get into the alveolar space and then breathe out. Okay? So this is how at the lungs oxygen gets in. So when oxygen gets in, it induces indirectly carbon dioxide disposal. So they are related to one another. Okay? So moving on to CO2 transport. So there are three ways for the body to transport CO2. And the three ways are here. Up to 10% CO2 is transported as is, because CO2 is 20% more soluble in water when blood plasma is 92% water. So that's why there's much more CO2 being transported as is in blood plasma than oxygen. 20% is bound to hemoglobin. And 70%, like I mentioned, is transported in the form of bicarbonate, HCO3 minus. Okay. Now, the difference here is, let's move to the tissues. Now we are at the systemic tissues. We are no longer the lungs. So what's going to happen is, at the tissues, oxygen will leave the red blood cell and go to the tissues. So you see here, this arrow here, that's oxygen leaving the red blood cell to get into your tissues. Now remember, this relationship is opposite now. So you have hemoglobin bound to oxygen, and at the tissue, oxygen is leaving. So oxygen is going out of the red blood cell to the tissues, and then it will leave hemoglobin by itself. And hemoglobin will bind to a proton back, that proton right there. Okay? Now this proton is from the relationship proton plus H3O2 minus. Now this relationship here has come up here, CO2 right here. So all of this is because CO2 from the cells comes into the red blood cell, interacting with water. Okay? And it gives H2CO3, carbonic acid, leading to the proton being released. And that proton will come and interact with hemoglobin, which leaves this here. It will leave the red blood cell, shown here, bicarbonate leaving the red blood cell. And when the cell is losing a negative charge, chloride will come in. The opposite. And at the tissue, this phenomenon here is called chloride shift. Okay, so at the tissue, we're talking about chloride shift. At the lungs, we call it reverse chloride shift. Okay? That's to basically maintain the neutrality of the cell. So when carbon dioxide comes in, it increases the bicarbonate leaves, and it's being transferred in blood plasma as bicarbonate. So this is how the cell is the body is transporting CO2. This CO2 comes from as a waste gas from cells. It will be converted inside the red blood cell. It becomes bicarbonate. It leaves the red blood cell as bicarbonate. So the gas coming into the red blood cells as CO2, but it's leaving the red blood cell. So CO2 coming into the red blood cells as CO2, but it leaves the red blood cell as bicarbonate, HCO3 minus, and it's being transported all the way to the lungs as HCO3 minus, 70% of it, okay? And in the meantime, when it does that, it induces, so when it comes in here, it induces, it interacts with hemoglobin, so it allows oxygen to be released, and oxygen goes into the tissues. Okay. There are two concepts related to this. I will explain it, but just in case it's not clear, um, I will give you the passage of the book where they specifically talk about this, the Haldane effect and the Bohr effect. And that's on page, let me see here. (488). The figure is 17.13. So page 488 of your Stanfield textbook. So let's start with the Haldane effect down here. The Haldane effect, to put simply, is the relationship between the concentration of oxygen, so low partial oxygen pressure, and it increases the CO2 loading. In other words, um, it facilitates CO2 transport. So in the lungs, if oxygen is high and CO2 is low, it promotes the unloading of CO2, meaning it facilitates the transfer of CO2 from the red blood cell into alveolar space. In the case of the Bohr effect, this is in the tissues. So in the case of Bohr effect, in the tissues where oxygen is low and CO2 is high, so the Bohr effect has the opposite function. It promotes the unloading of oxygen. So it basically, because when CO2 is high, it affects the pH, right? So when CO2 is high, it will increase the concentration of proton, and that leads to the Bohr effect, meaning it will induce hemoglobin to unload oxygen to the tissues. Okay? So when CO2 is high in the tissues, it induces oxygen unloading by the red blood cell to the tissues. So it makes sense when you think about it. So at the tissues, CO2 is always higher from the tissues than in the systemic capillaries. So if that's the case, that it induces the gas exchange, oxygen will go to the tissues, CO2 will go to the red blood cells. And the reverse at the lungs is when oxygen is high in the alveolar space and low in the oxygen red blood cells, and CO2 is high in the red blood cells and low in the alveolar space. So it induces unloading of carbon dioxide and picks up oxygen. And that is described on page 488 of your Stanfield textbook. But what is important is not about the Bohr effect or the Haldane effect. I want you to understand that equation at the center of it all. Again, that equation, CO2. I cannot stress the importance of this equation enough. CO2 interacts with water, combines with water to form carbonic acid, H2 CO3. And again, like I said, this is in equilibrium, so it can go both ways. Same thing here, both ways. CO3 minus bicarbonate plus the proton. Okay, and this is basic chemistry, and this is how it works. So let's say if CO2 increases, it will drive the equilibrium this way. It will cause the proton concentration to increase. And that, if that's the case, then pH drops. You have acidic pH. You're just acidifying your solution. Okay, again, if CO2 increases, then proton increase, the concentrated proton increase, and pH drops. Now let me use another color. Let me erase this. And use another color to highlight the concept, black. If CO2 now drops, then it's create the opposite direction. Proton will drop because proton is being used to drive the reaction. So what's going to happen when CO2 drops? This here, pH increase. The pH of the solution becomes more basic. So that's why we say equilibria here, because that the arrows can go from, if CO2 increase, it moves from your left to the right, and if CO2 decrease, it will move from the right to your left. So make sure that you have that. Not only, I know that you have open access to everything during a test, but it's important for you to understand the concept, right? Because when I write that test, I design that test, and I know that you have access to everything. So I want to test your level of understanding about it. So make sure that you understand the concept, the relationship between CO2 and the hydrogen ions, the hydrogen cations. We call it a proton, okay? So moving on to how we control ventilation. They are detected by chemoreceptors. These are peripheral chemoreceptors. They're located, for example, in the carotid bodies. So in other words, right here, this is right before the common carotid splits, bifurcates into internal carotid and external carotid arteries. This is from anatomy. So there's a ballooning structure in the wall. We call that the carotid bodies, and they contain chemoreceptors that are sensitive to CO2. And this is amazing. The body is more sensitive to CO2 than oxygen. The body basically kind of ignore the concentration of oxygen unless oxygen drops below 80%. And you can see it right here. So from 80 to 100 millimercury is flat. The body ignores it. It becomes sensitive to oxygen only if the oxygen level gets below 80. So from here, okay, if below 80, then you see that curve going up. Okay, so the lungs will basically take over. However, during that same conditions, look at the CO2. It's extremely sensitive, much more than oxygen. Okay, now, what is amazing is when we talk about the body being sensitive to CO2, there's a catch to that statement. And the catch is when you look at the central nervous system in the cerebral spinal fluid, the CSF, right? This CSF here, since CO2 is directly, related to the pH of a solution, that's why the brain specifically is extremely sensitive to CO2, because we learned earlier, CO2 is directly related to the pH of that solution. So if CO2 increase, proton concentration increase, pH drops. Okay, so let's write that out. If CO2 increase, pH drops, and that's deadly for the brain. So that's why CO2 is exquisitely, controlled in the brain. And same thing happens here. CO2 is leaving and it's converted to proton. So as you see, it's very dangerous. So CO2, if CO2 increase, you have free floating proton increase. You never want that to happen. So that's why it's highly regulated. So as soon as CO2 is elevated, it induces oxygen unloading, right? So it facilitates also CO2 being picked up by the red blood cell because of that relationship. So CO2 and pH and oxygen and hemoglobin. So the more oxygen is disengaged, detached from the hemoglobin, it allows the hemoglobin to capture the proton. Okay? So to summarize, peripheral chemoreceptors are located in the peripheral nervous system. Central chemoreceptors are located obviously in the central nervous system. But the difference is the chemoreceptors are sensitive to CO2. Peripheral chemoreceptors are sensitive to carbon dioxide. But the central chemoreceptors are sensitive to pH, which is indirectly also sensitive to CO2 because CO2 is related to pH that I talked earlier. Okay. The reason why they're sensitive to pH is because pH is deadly. You acidify and in the body, the pH homeostatic level is really narrow, 7.35, tightly regulated to 7.45. Okay. So if you go below 7.35, you have acidosis. And if you go above 7.45, you have alkalosis. So only within this window, this narrow window, that's where we have homeostasis. So that's the homeostatic pH window, right? So this is the healthy, normal pH window that the body tolerates. Below 735, acidosis. Above 745, alkalosis. Moving on to this one, there's a coupling going on between ventilation and perfusion, meaning the amount of air available in your alveoli will basically have a direct correlation between the amount of blood flowing in the pulmonary capillaries for gas exchange. That's what we call a coupling. The more ventilation, the more oxygen present, the higher the perfusion. The less oxygen, the less perfusion. And we call it ventilation perfusion coupling. Let's go to the next slide and I will come back to this one for the detail. So let's say here, in this alveolus, air has been compromised, right? So the alveolar ventilation is compromised. Alveolar ventilation has been decreased. So what's going to happen is from here we start decrease in ventilation will lead to a constriction, vasoconstriction of the blood vessel. So there's less blood flowing through that particular location. And think about it. If there's less air in that area, blood will be diverted, right? Blood will try to go to where there's more air for gas exchange. In this case here, this is when the alveolus has normal, ventilation. Then what's going to happen is the blood vessel, the capillary bed, will dilate out. So to allow more blood to flow in, because there's a lot of air to be exchanged. So if you allow more blood in, there's more gas exchange, right? So you allow more carbon dioxide to be disposed of. You allow more oxygen to be picked up. So this is why we call it ventilation perfusion coupling. So the amount of air in each alveolus would dictate the blood perfusion of that capillary bed that is perfusing that particular alveolus. And from anatomy, you should notice the surface of each alveolus is basically covered by blood capillaries. And not only blood capillaries, it is also covered by elastic fibers, allowing the alveolus to expand and recoil, right? So when you're breathing in, those elastic fibers allow each alveolus to expand because air is coming. And when you're breathing out, those elastic fibers recoil to help pushing air out during breathing out, during exhalation, right? So when that air is available, blood vessels will dilate, vasodilation, increasing blood perfusion, increasing blood flow to that particular alveolus, to increase oxygen transfer from the alveolar space into the blood capillary, and to increase the disposal of CO2 from the blood capillary into the alveolar space. If there's not much air in that alveolus, the entire capillary bed surrounding that alveolus would be constricted, vasoconstriction, to decrease blood flow to that particular alveolus. And that blood will be diverted to other alveoli that have proper ventilation. So that concept, again, the relationship between ventilation in the alveolus and the blood perfusion in capillary, we call it ventilation perfusion coupling. And that's all that is detailed here in writing, okay? So low alveolar PO2 due to inadequate ventilation, meaning air in that particular alveolus is compromised, then the capillary bed, the arterioles constrict, decreasing blood flow because there's not, to basically save that blood, divert that blood to where there's high alveolar um, um, ventilation in another alveolus so we can have gas exchange. Okay. In the case high alveolar PO2, this is, yeah, this here should have been, okay. High alveolar PO2, bronchioles dilate leading to increased CO2 elimination, because what's going to happen is if you have a lot of air in the alveolus, blood capillaries will basically, the arterioles upstream of the capillary bed will dilate. So more blood will flow into the capillary bed. Oxygen will move from the alveolar space into the blood capillary, and CO2 from the blood capillary will be leaving the blood capillary to go into the alveolar space for disposal. Okay, so that is the ventilation perfusion coupling, the direct relationship between the amount available of air for gas exchange and the amount of blood flow in the capillary bed. If ventilation increase, uh, if amount of air is available, then blood perfusion increase. If ventilation drops, blood perfusion drops. Okay, so if the alveolus is properly inflated, vasodilation in the vascular bed. If the alveolus is underventilated, vasoconstriction in the capillary bed. And on that note, I will terminate today's lecture.